Hey, welcome back. This is a shop talk for April 2025, and I have a few things that I wanted to show you and maybe a little trick in regards of machine alignment. So first of all, I rearranged the side of the shop. As some of you might know, I have two separate rooms. Well, they are connected, but they are kind of distinct rooms. In here I have the workbench and my two main manual machines. I will show you a picture of the arrangement before with the Deckel FP1 mill to the left and the Weiler lathe to the right. I was never overly happy with this arrangement. It was just a little bit too cramped, and the storage between those two machines for accessories was not great. So I already was browsing eBay for used drawer cabinets like a Lathe or a original Deckel accessory cabinet, but then I was reminded that I have an original Deckel 5-drawer cabinet in the basement. Picked it up from my old day job years and years ago for basically free. And it sat in the basement. It was very rusty and in really rough condition. So took it apart, sanded it down, put self-etch primer on it, painted it in 6011 Reseda green, put new bearings in for the drawer slides, welded up a frame for it to sit higher and also to be able to be pallet checked around. Added a nice wooden top to it, and well, it's sitting here. And the lathe is not here anymore. I took the lathe, picked it up with the pallet jack. The lathe is very pallet jackable, to be honest. It's very easy to pick up and move around. So I moved it from here, turned it 90 degrees to my left, standing right in front of the window. And this kind of opened up this entire, not very big space. And I have a small drawer cabinet left to the lathe. I have a cabinet with the surface plate to the right of it, which I will talk in a second about. And overall, I'm extremely happy with the rearrangement. And despite being a very small change, I basically just took one machine, turned it 90 degrees, and that's it. And added this cabinet here. This made a huge difference in overall, I wouldn't say efficiency, but in my happiness of using this room. This cabinet now has all the accessories for the milling machine, plus some of the work holding for the CNC, because those two machines share the same quick change tooling for work holding. Yeah, these drawers are fairly loud, and that's just to the nature of it being ball bearings running on folded steel. That's just what it is. But you can put quite the load into these drawers. I have the quick change vises in here, the adjustable 3-jaw chuck, the small lang vise, all the jaws. Back there is grinding vise. This lower one can even hold the XY table that goes on top of the indexing head, angle plates, some colored blocks, a staircase, strap clamps. Things like that. Collets. I still need to make the inserts for these tools so they don't rattle around. This is not ideal yet. These are original drawer inserts from Deckel. These are quite nifty. They nest into each other, or on top of each other, and you can slide them on top of each other to access the tools below. This one is original. I modified it a little bit to have the wrench for my self-centering vise in here, and also to have a spot for this wrench. These are the wrenches for the mill arbors, a set of Allen keys, and down here I have regular wrenches and torque wrench. Torque wrench is for the Lang quick change plate. Let's have a look. This is the original catalog, even in English, for the tool cabinets that Deckel sold for the FP machines. And this is the full layout. This is the throne of Deckel accessories. You have the large central cabinet and 2 accessory cabinets to the side. And you could mix and match them as if you wanted, depending on what accessories you had. This is all you needed, including the cabinet for the boring head and the grinding head, the jig grinding head and the jig boring head. So this is the small cabinet it's like a garage door with a rollout cart that could be accessorized differently. Could hold the slotting head, for example, and the indexer on top. Or, for example, the large swiveling table for the bigger machines like FP3 and FP4. And the drawers could also be individually equipped with, depending on what you needed. Arbors, sleeves, the rings for the mill arbors. And it was a very, very complete setup. Even the 380mm rotary table could find a spot in these cabinets, which is quite impressive. Or the optical rotary table. I'm not entirely sure which rotary table this is because it came, I think this is a very late rotary table for the jig grinder because it has a Heidenhain readout, a single axis readout sitting back here. I have to do some investigation on this one. Different chucks for the indexer. This is the coordinate, the XY slide for the indexing head that's used for punch milling. And now we come to the large central piece, which looks like this. And this holds everything. Even the spiral milling attachment, slotting head, regular milling head, the overarm supports, rigid table, the indexing head. Down here there's the big rotary table. It's comical what they fitted in there. So yeah, that's the Deckel tool cabinet for FP machines. Brochure. And yeah, that's the arrangement on this side with the lathe in the center. And the window in the background is really nice it's a nice glimpse into the outside world while you're working here. The surface plate on the modified tooling cart. This, one might think, yeah, that's a problem, it will get chips and dirt all over it. But the reality in a small shop is wherever you put the surface plate, you will get dirt on it. You need to clean it, and the tesa height that's sitting on it needs to be cleaned or covered if you're doing really dirty work anyways. While I was rearranging my shop, I also took an effort in cleaning out and organizing my metrology tooling. And in the past I had been very vocal about not liking foam inserts for drawers. But now that I have a sponsorship with a foam cutting company, just joking, I made these myself. I figured I'd try this for myself, if I like it. I just took the high density foam. I bought this from a Hobby M machine. I will put a link to the foam in the description. A full sheet of it is like $9, relatively affordable, and it's very easy to mill. You can cut it with a circular saw or a table saw, and you can mill it with any woodworking router or a CNC mill. And I figured I'd try it with my most used metrology tools, like calipers, my 2 quantum mics that I use all day. Precision straight edges, some squares over here, combo square, dividers, my depth micrometer and its accessories, universal protractor, and this is not, well, it's a metrology tool too. This is the low profile V-block that Adam sent me, which is, I really enjoy using this. My precision magnets, my tool room magnets go here. A small sign bar goes here because that's stuff that I use all the time. Back here I have 2 boxes. One is, these are extensions for indicators, and in here these are all different tips for indicators. Flat, round, extended. These are lifters. You put these on the stem of an indicator to lift the stem. 2 different magnifiers. This one has a reticle in it to measure distances and radii. This is just a 7x loop that I use every day. Second drawer, 3-point internal micrometers from 6 to I think 20 millimeters. Disc mic, universal micrometer or unimic. 2-point internal micrometer. I made these years ago. These are just nice 45 and 90 degree angle blocks. 1 micron Hicator, 2 micron dial test indicator. In these 2 spots, normally 10 micron indicators live, 1 in a jig bore style and 1 in a regular style. Cheap protractor, some low profile V-blocks. I took some regular V-blocks and I cut them down in height, and I kept the offcuts. These come in relatively useful from time to time. Back here, just some accessories, radius and thread gauges, feeler gauge, another set of radius gauges. Mitutoyo micrometer set from 0 to 150 millimeters. In here, there is a spare Mitutoyo dial caliper, if I drop my other one. And in here, I have the standards for the micrometers. So yeah, the foam was very easy. I don't enjoy doing CAD for this type of work. The most common way of doing this is to lay out the tools as you want them, take a photo from above and trace out the contours from the photo in CAD and then go from there. Or you measure everything and draw the rough shape in CAD. That doesn't sound very enjoyable to me. I just placed the tooling on the foam, took a silver pen, paint marker, traced around it, and I took a handheld woodworking router, a trim router with 6mm single flute end mill, and I just routed it out. Cutting out the foam with the Makita handheld router, and you can see me doing a kind of spiral motion to move along the contours that I have drawn onto the foam. This is me imitating a roughing tool path of a CNC milling machine. After that, a slower, more defined contour path just to clean it up. Here you can see the roughing process close up again. It's quite a messy process. A dust mask and hearing protection are a good idea, but that's common sense anyways. And yeah, it's not super clean. You can see, for example, here on this pocket for the jig bore style dial test indicator, it's not super clean, but the overall impression to me is I'm happy with it. It looks fine to me. I open the drawer, I see everything, and my main concern was, yeah, but what if I get a different tool and have to replace something? Well, I can always cut out a chunk of the foam and put a different piece of foam with a new insert in it. The point with not enjoying the CAD portion of making drawer inserts, that's also why I'm not big on 3D printed drawer inserts like Gridfinity. I simply do not enjoy modeling drawer inserts. Feels I prefer to be in the shop and make chips. And on some of the pockets here, I milled portions of the contour deeper to allow me to release the tools if necessary. Some of them are easy to grab, some of them have the pocket to tilt them out of the pocket. So yeah, that's my 5 cents on foam drawer inserts. To the right hand of the lathe, which is right behind me, I have 2 tooling cabinets. This one has the surface plate on top of it, and this one just is a tooling cart with all my hand tools in it, like files, pliers, hammers, and just the regular hand tools. But you might notice this one has wheels and this one doesn't. Since this has the surface plate on top of it, I modified it to be a stationary cabinet. This reduces wobbling around quite a bit. So took off the wheels, I welded up a frame, painted it, added adjustable feet to it so it can be leveled, added a wooden top of it, and to place the surface plate on top of it, I drilled 3 pockets into it with a Forstner drill, a Forstner bit, placed 2 washers of different size in it, a large flat washer and a smaller washer with a spherical pocket. That's a standard off-the-shelf item. And the spherical feet of the surface plate nest into the spherical pocket of the washer and allow the surface plate to slide around with heat expansion and contraction. So it's not influencing the precision of the surface plate. Surface plate sits on 3 feet and the 3 feet can slide ever so slightly around. We'll show you that in a second. In here you can see that's the foot of the surface plate. The surface plate comes from factory with 3 feet glued onto it. That's where the surface plate rests on when they lab and inspect it for final precision. And when I push sideways or pull on the surface plate, you can see that it's moving very freely for a quite decent amount. I think it's a decent compromise without having to go through the trouble of building a full-on surface plate stand with 3 mounting pads. Sketch of the foot pad arrangement. Up here, surface plate. This is the glued-on spherical foot. And down here, this is the wooden top of the cabinet. And this is the drilled out pocket. Just used a large Forstner bit in a cordless drill and calipers to get them all to approximately the same depth. Then I have a large washer, just cleaned them up with the magic sanding plate on both sides so they are flat-ish. Place them in there. Then I have a second washer. This is actually a fixture washer that you would also use on a milling machine for setup. These are fairly thick. They are heat treated and they have a spherical pocket on one side to match up with the spherical face of fixture nuts. Probably not telling you something new here, but for setups, this is a good combination. You buy these nuts with a spherical face and these heavy washers, and this allows for angular misalignment between the stud and the thing you're clamping on. Very, very useful for safe and proper setup. And I took 3 of those washers, drawn here in green, as an interface between the large washer and the spherical foot, and this can slide around. I put some molybdenum disulfide grease between those two to reduce the coefficient of friction. And yeah, this feels, I have a good feeling with this setup. Means that if the surface plate grows or shrinks with temperature change, I'm not creating any weird tension in the surface plate. The surface plates stay flat with changing temperatures. If the room is 5 degrees or 55 degrees Celsius, it doesn't matter for the flatness of the surface plate. What matters is if there are weird forces pushing on the feet or a temperature gradient in the surface plate from top to bottom. If the top is warmer than the underside or vice versa, the surface plate will warp like a bimetal strip. That's also why companies like Moore went through so much trouble with their in-house production facilities to have very even temperature gradients in their production rooms. If you want to know more, I recommend you the book Foundations of Mechanical Accuracy from the Moore Company. So yeah, that's the foot setup. That's the corner with the two cabinets. It all came together really, really well. The metrology cabinet clears the hand tool cart ever so slightly. There's like a 10mm gap between the drawer and the other cabinet, and that makes me very happy. Oops. Over here I have all my hand tools. Mostly, I'm not a big hand tool guy. It's kind of mess, to be honest. The important stuff is sorted to get me along, but yeah. And I have this dead corner, of course, between the two carts, and I figured I can put the oxy fuel cart back there, and the hose reaches all the way over to the workbench if I need it for brazing or liquefying a screw. Quick look in the corner. There's the oxy fuel cart. I have repeat work that requires me to set the angle of the compound slide to a very precise angle. And the best way for me that I found is to use a sine bar. It's a little bit more effort, but gives me very good results. I have two ground tool room magnets on the back side of the compound. I know that the backside of the carriage is in line with the axis of the travel of the compound. You can just put an indicator against it and crank the compound back and forth, and when you don't get a reading or a deviation on the indicator, this is parallel to the travel of the compound. That's something that you have to check before you use this technique, and if there is an error in the parallelism, you have to mill or grind or scrape one side parallel to the travel of the machine. The ground magnets I'm using, I have a video on making these. Well, I think it's a two-part video series. You can buy them commercially. They look like this. They are ferrite magnets and soft iron laminations stacked up against each other, and they are contained on two sides with soft steel. Super expensive. If you buy them new, they are in the €300 range, but super useful. These followed me my entire professional career, both for machine setup, assembly, and also on grinders. And then I have a sine bar. I made these sine bars in 2016. There is I think that's also a video series on making these. That was the time when I still was doing 17-part video series and didn't know how to edit short form videos. And the gauge block stack back here. And to keep it all together, add a rubber band. Otherwise, the sine bar, you always have to make sure that the sine bar mix with the rollers, contact with the gauge block stack and with the magnet. On the magnet it's easy because it's attracting the sign bar by itself, but against gauge blocks it's a little bit tricky. So adding a rubber band around everything gives you a nice solid contact, and you can run your indicator along here to indicate the axis, or to indicate the sign bar through with the carriage travel of the lathe, and this gives you the desired angle on the compound. Of course, you have to do your math on the angle here. Sign bar calculation is fairly simple. It's the sinus of the desired angle that you need or want. In my case, it's 47 degrees. We take the sinus of this, then we multiply it with the distance of the rollers, which is 50 millimeters on the sign bar, times 50, and I get a gauge block stack of 36.568 millimeters. Cut off the last numbers to 4 digits, and then you round to 3 digits, so 36.568. And that's the gauge block stack that I have against the magnet and the sign bar. I'm going to use the 10 micron G-rod dial test indicator. Once I dialed it in with this, I will compare it to the electronic indicator, just for fun, just to get you an idea how good a 10 micron indicator is, or can get you. There are distinct quality differences between dial test indicators, but I found that the Mar, Mitutoyo, and especially the Giro, oh god, it's probably the French part of Switzerland, so I'm completely butchering this. These are really nice and very economical from a price standpoint. So this is not aligned properly yet, so I'm going to tap it in. We start, let's put in a number that we can follow. Put it at 30. And the needle rises ever so slightly. I'm just using the handle of a hammer, because that's easy to reach around the indicator stand. Still rising. Okay, adjust it to 0, well, to 30, and now it's not moving anymore, as far as I can tell. Put the electronic indicator on here, and when you set up an electronic indicator, you always make sure that the cable is not influenced by any of the motions you're going to take when indicating. For example, having the cable drag on the carriage, because an electronic indicator is so sensitive, the force from dragging the cable around will influence the measurement. It's currently set at 30 microns, plus minus 30 micron on the upper scale. So 3 up here is 30 microns. Bringing it into contact, that's kind of a very useful range. 60 micron total range. That's for general machine shop purposes quite nice. It's still a good range for alignment, but it's already very, very sensitive. I got it in contact, and you have a little bit of electronic adjustment for 0 here. Now we'll touch the cable or move the cable around. And as you can see, the needle moves all over the place. That's me influencing the indicator just by moving the cable. Or for example, this is my tweezers when I rest it on the indicator stand. It's already moving around. Gets worse when you put it into a finer increment. This is plus minus 3 microns, so 10 times more sensitive. And as you can see, it's going all over the place when I get my tweezers on here, or if I move the cable around. So I indicated the compound in with the 10 micron reading dial test indicator, and now I'm using the electronic indicator to compare my result, to validate it. So we start here. I'm moving over. And the needle has barely moved off 0, so we definitely can go to a tighter resolution. Now we are plus minus 10 micron over the entire scale, so that's the lower graduation here. Now we see things like the gear train, the carriage gear train moving the carriage around. That's the needle jitter. So we start at minus 1, minus 2, and we kind of raise to plus 1 and a little bit maybe. So the reversal check, we start at plus 1 and we drop to, we're at about 0. So yeah, there is a little bit of, since it's a box way, like any sliding element weighs, there is play in it. There's a little bit of play, but as you can see, we got it really, really good with a 10 micron indicator. There is often no need for a more sensitive dial test indicator in a normal shop. So a 2 micron or 1 micron dial test indicator is often on a normal machine tool that's not a grinder kind of overkill. We can do this even funnier in the plus minus 3 micron range, which is the finest setting this will go to. Zero it out, and yeah, now we see a lot of movement. That's mostly in the gear train. There is an ever so slight tendency to rise, so the compound is a little bit in this orientation. I will give it a little bit of a tap just to get a little bit better. That's looking quite nice. A tiny tap. And also, when you tighten the screws, you will see also some movement. Especially if you try to tighten one side fully and then the other side, then you will get a lot of movement. Well, a lot of movement is relative. You will get some movement. So double check. Let's go to plus minus 10 micron. This is less irritating. Yeah, that's fine. Since the taper I'm turning is only 3 millimeters long, this is fine. But yeah, goes to show. The electronic indicator is very useful because you can jump between resolution very easy. You can do super rough alignment when you put it to 1000 micron, full, plus minus 1 millimeter full travel. Or you can put it to 3 micron plus minus full travel. So I think that's the great power of these electronic indicators that gets overlooked quite often. Yeah, they are super useful for high precision work because they are super sensitive. But also they are super handy because they are super quick to adjust in their sensitivity. That's what makes it valuable to me. And it's a nice instrument. And this is the part I did the setup for, a small aluminum cone. Here I'm using a standard carbide insert to rough the cone shape in one pass. The liquid I'm using is isopropyl alcohol for lubrication. That's the roughing cut, and I'm changing over to a MKD insert, which is monocrystalline diamond. This is just a chunk of diamond braced to a carbide carrier and then lapped sharp and into shape. This one is from the company Contour Diamonds, and they're fairly expensive, but the finish they leave is amazing. And again, using isopropyl alcohol as a lubricant. I'm doing two passes, one with about 0.1 millimeter depth of cut, and then a second pass with 20 micron depth of cut. These cones go into an optical device with laser application, and it's kind of a repeat work that I do. If you have been with me for a certain amount of time on this channel, you might have seen this tool. This is my indicator holder that I made probably something like 12 years ago. Didn't film it, but I put out a set of drawings to make one yourself, and I know for a fact that a lot of people have made these. I think it's a great, like a first project for a home machinist. A lot of things you can do on these to learn certain skills. And you end up with a super useful tool that lasts a long time if you don't crash it, like I did. So this is basically meant to hold dial test indicator like this. This end goes in a collet, and you can sweep bores or a round feature on a part to locate your machine to the part, which is very important in machining. Also, it can be used as an edge finder or to center stock to the spindle. But as I mentioned, it lasts forever if you don't crash it, and I certainly did crash it. As you can see down here, there is a dovetail that interfaces with the dovetail of the dial test indicator holder. And, well, it's only a half dovetail anymore. This is a fairly thin section of metal, and it broke away when I spun the indicator housing against, I think it was a vise jaw. And it levered this dovetail open and broke this piece off. I didn't come up with this design of a indicator holder. This half moon shape is fairly common available as an industrial item. What I changed was the end here to hold dial test indicator. Commercial ones have a rather odd solution that I did not like very much. I copied, because it's hard to come up with something yourself. I copied the design that Mar uses for their indicator snugs. This has an 8mm shank and can go, for example, in a height gauge. And this side is to hold the dial test indicator. Dial test indicator slides in and it locks up with this knurled, fine threaded nut against the dovetail. And I think it's a quite nice design. This holds the indicator quite well. And you can make the dovetail fairly sloppy, since the nut always pushes the dial test indicator outwards and locks it very nicely into the dovetail. That's kind of important because the dovetails on these dial test indicators are not overly precise. And that's what I copied on my own design. As you can see, here is the knurled nut. And here you can see where the wing of the dovetail broke off. I lived without this thing for quite some time now, and it's really getting annoying. I helped myself with a flex arm Noga indicator holder, but those are really not great. They have way too many degrees of freedom to work quickly. Really a pain to adjust nicely. So I wanted to have this back, but didn't just want to rebuild it. I want to make it better. So I figured some kind of a fine adjust to be able to locate or position the probe tip of the dial test indicator without having to fumble with the lock screws would be nice. And I came up with this. This has the same taper seat that the original design has. I still had the original D-bit reamer that I made like 12 years ago. This is ground out of high-speed steel. Has some nice coloring. By the way, high-speed steel doesn't really matter if it gets a little bit of color. It takes a little bit more to get high-speed steel soft. I machined it out of Toolox 44, which is a heat-treated tool steel. Comes in at 40-ish Rockwell C, so it's still rather soft, but very strong. I added a slot in here and a flexure up here. Flexure is basically a solid material hinge. It's just bending the material to create a hinge with no play. And I just had the CNC cut this shape out of a piece of Toolox. This is the CNC cutting the prototype for the fine adjuster. First tool is a 6mm carbide end mill that I'm using for roughing in this case. And changing tools. The HSK quick change spindle has proven to be very nice for my purposes, despite people telling me that I bought the wrong thing. This is a 2mm 3-flute carbide end mill with a neck length of 20mm or 18mm, something like that. And I'm just stepping down the contour of the fine adjuster, including the flexure slot. Walking down in 50 micron increments, taking it slowly, really not a problem. Long-necked end mills like that just take their time. It is what it is. The final design of this fine adjuster will be machinable with manual machines. It will not be trivial, but it will be very doable. This is a relieved 1mm ball end mill to cut the flexure slot, what will later be the clamp for the dial test indicator. Since the part was already set up in this orientation, I figured it's easy to just use the ball end mill and cut the slot this way instead of doing another setup on a manual mill and using a slitting saw. Then I did the remaining mill work, like the dovetail or the taper seat on the other side, on the manual mill. For the fine adjust, I drilled and tapped it with an M4 thread here on the back. And the way this goes together is there is a small ball bearing ball which drops in here, and a thumb screw, which is just a regular M4 socket head cap screw with a pressed on 3D printed knob. These knobs can also be purchased by a company called Shearlock, but they're a little bit hard to get a hold of here in Germany, so I 3D printed this one. And as you can see, the bearing ball in here rests against this part of the indicator holder, and the screw presses against the ball. So I have this point contact area, and it's fairly nice to adjust. My first design, the flexure beam up here was 2 millimeter thick, and that was really much too thick. It was really hard to adjust, so I came in with firm the outside with ball end mill, and I thinned this area down to 1 millimeter. So it's 1 millimeter thick, and I think it's 12 millimeters wide, and now it's rather nice, adjustable. But the M4 screw is a little bit on the coarse side. So I figured I could make a fine set screw or a fine adjust screw, or I go on the internet and I purchase a fine adjust set screw and nut from Thor Labs. These are used in optics, for example, to adjust something like a mirror, I think. But these are really nicely made. They are not overly expensive. I think the screw is like 10 bucks and the nut is also like 10 bucks. They get you with shipping. Yeah. In the end, it's fairly expensive to buy stuff, but it's really nice. And for a change, it's cool not having to make everything myself. Also, I ordered, they make an aluminium thumb screw that threads onto the set screw to make it into a thumb screw. And I want to put this in the next version of this indicator holder instead of a regular M4 screw. If you want to make one yourself, you're of course free to choose. Do you want to go with a regular standard thread adjuster? Do you want to make your own? Do you want to purchase a fine thread screw? Or do you want to purchase one of these guys? I will release the drawing once I have a final version of this, of course. And also I changed how the indicator is held. I oriented myself with my low profile dial test indicator holder that I made a year ago. And this has just a split clamp arrangement to hold dial test indicator. It's split here and split here, so there's just this short bending beam in here, and dial test indicator goes in here, and it gets pinched by a cross screw. So this is also a very, very robust and very solid clamp arrangement. So screw goes in from the side, locks the dial test indicator. As I said, the taper seat here sits on these tapered pins. Goes on like this. 2 Belleville washers. I added these a few years ago to this design. I think it's a little bit nicer. A nicer lockup, and you get a little bit of travel with the locking screw. You can go in, then the springs are preloaded, and then you have a little bit of adjustment here. Then you can fully tighten it down, flatten out the Belleville washers. They won't do anything. They will behave like a hardened washer at that point. Then the thing is locked in position. The dial test indicator, of course, goes in like this. This is a vertical dial, jig bore style of a dial test indicator. Doing this around the camera is really, really fun. So this locks in here like this. And here's the modified dial test indicator with a fine adjuster down here. Let's put it in a milling machine and see how the fine adjuster affects the position of the probe. Here we are at the milling machine, and I'm still figuring things out with this new design, learning what I built here. The fine adjust is more for bringing the dial indicator into contact, not to really zero out the dial. Zeroing out the dial is really best done just by moving the dial. Here we can see the range of motion that I get out of this style of dial test indicator in combination with the fine adjuster. The range of motion of the probe tip, of course, changes with the overhang of the indicator. Let's put a scale here. With the fine adjuster fully backed off, putting a scale here at 80. And I tighten the screw as far as I'm comfortable with, and I get about 4 millimeters of movement of the needle. I think that's respectable for a fine adjuster. And as I said, it's really just to get the probe into contact with the work without having to mess with the joints of this thing. So you roughly get it in contact, and then you just get it fully preloaded, set your dial up here to 0 or whatever number you prefer, and you're good to go. This is an overview on progress on this tool. Very low key working on it. Now that my kitchen remodel is done, I can spend a little bit more time on personal projects again. The fine adjuster probably will stay this shape. I have to tweak a few dimensions, but I will add a eccentric adjuster for the shank up here, because when you indicate very small bores or use this as an edge finder to sweep edge of a part, it's very annoying if the dial test indicator is offset to the side in relation to the shank. So an adjustment to get the shank in line with the probe tip would be very much appreciated. On the low profile dial test indicator that I made and released drawings for, and I'm very happy with the functionality of that. And I want this on this holder too. But Stefan, why are you not just using the low profile dial test indicator on your manual milling machine? Well, kind of two different applications. The low profile dial test indicator holder. This is the low profile dial test indicator holder that I made. And as you can see, this is really designed. This is designed to have, as the name implies, a very low profile, and it works really, really well for this. It's great for picking up bores, workpiece edges, but it can be tricky if you have features that stick up out of a part, to clear those features, because the probe is extending only like 10 millimeters out the bottom. And then you have all this stuff here. So it's a little bit hard to clear certain features, and that's where this design comes in, which is highly adjustable. You can tilt the indicator in all orientations. You can use either a chickbore style dial test indicator or a regular one that goes out this way, and you just have a lot of options. Since it can kind of fold up in itself like this, you can move it like this, you can tilt it outwards, you can put it upside down, flip the indicator around and get a very large arc. So it's kind of two different tools. They serve generally the same purpose, but the actual use is very different. This is more for the CNC, for smallish parts, and this is more a general use tool for the manual mill. I wouldn't want to be without either of the two now that I have them, especially this one on the CNC is really, really quick. The adjuster here works so well. So yeah, I'm playing around with designs. This will stay here. I made this November 2023, and I wouldn't change anything apart from maybe cutting this corner just to make it look a little bit nicer. But apart from that, I'm very happy with the overall design. Wouldn't change anything so far. A piece of tooling that I wanted for quite some time is also a bit of a luxury item. At my old day job, we had one of these in the welding room, and also some of the mold makers had these on their bench. What it is a spherical body with a switchable magnet in it, in a ring base with leather padding. These are usually really, really expensive, and this was also really expensive. Normal list price is somewhere in the €1,000 range for a 80mm diameter magnet. When I was at the Intec trade show, I saw the booth of Flake Magnetsysteme, and they had one of these on display. I got to talk with the guy on the booth and asked for the price, and it was like €700 before tax. And yeah, that's a little bit less than most of the other people ask for these, but still a lot of money. And then he mentioned that they have scratch and dent ones in store, at least one. And then he can give quite a discount on one of the scratch and dent ball vises. And yeah, they sent me the quote for one of these after the trade show as scratch and dent, 50% off. And well, I ordered it. It had one severe dent here that are already filed down. The body of these is aluminium anodized. And by the look of it, it literally fell off the table onto this edge here. The magnet itself is embedded into this aluminum body. It has a hex drive here. Turn it on and off like a regular magnetic chuck on a surface grinder. And you just put a part on here and it's held in place. And what do you use these for? Well, you use them for example, for deburring, for detail work. At the day job, this lived a lot of the time in the laser welder, because it's very easy to orient parts in the laser with this. Also, some guys used it for TIG welding, doing weld buildups on dies, and it's really useful. It's very simple and very fast. You don't have to lock anything. It's just held down by gravity in this ring down here. Engravers use very similar ball vises, but often the upper part of the vise is, for example, divided into two and has a ball bearing in it, so they can spin it very freely when they have to chase a radius or a curve or a spiral with their hand graving tool. There are DIY versions of these. There are also versions that instead of a magnet have a vise, sometimes with universal jaws that have pins. You can get those relatively inexpensive on the internet. Ball vise or engraver's vise is probably a good search term to start looking for. But I wanted a magnet, because most of the parts that I do are non-magnetic. This seemed to be the most logical choice. I like magnets, that's the real reason. And well, you can put parts on here, put in here, and then you can take, for example, your die grinder, a little bit of something like a sock filled with sand, or a sandbag. A shooting stock would be very nice to rest the hand on. Just a piece of wood is a little bit a little bit harsh. Or just a rag can also work as a rest. Just like this, and then you have all of the part that's not held directly on the magnet accessible just by orienting the magnet for deburring. And this works really, really well. It takes a little bit of practice and getting used to it, but do one side. Back side. And when you're done with your motorized deburring, you can always come back with stones and refine your deburring in those areas that you could not reach with the die grinder. So now you think, well, that's a magnet, it's holding only steel parts. Yeah, but you can not only hold parts with it, you can also hold work holding with it. For example, you can put a V-block on here, if you so desire. And you can hold, for example, a round part in here. This happens to be a welded socket extension, so maybe a good example. For a DIY ball vise, if you don't want to make a ring with a leather pad, you can also use something like a sandbag, like a small cushion filled with sand, and you just nest the ball shape in it, or a small rubber tire from an RC car, or from some small apparatus, just a small rubber tire. And that was Adam the Machinist's recommendation for a DIY one. As for finding a nice big sphere, well, you could buy spun sheet metal half spheres, weld them together to form a ball and fill them with sand, epoxy, concrete to give it some weight, then add some means of a fixture plate on top of it, for example, if you don't want to integrate a magnet or a small vise, something like that. Or you make a pitch fixture that's with soft pitch that you stick your part to. Many options. Or you scrounge the battlefields and find an old cannonball that's also round. Or if it can be bigger, you take a bowling ball. Don't steal the rental bowling balls from your bowling alley. I don't think that they like that. And saw off the top. There are some cast iron spheres, decorative spheres, or boccia balls. I think there are some large metal spheres out there that you can use. Don't use demon core. Yeah, but I'm really happy about this. This was a very happy accident that I got this for reasonable money. This doesn't help you, of course, because I don't suspect that they have a lot of scratch and dents, because somebody will ask in the comments who I got this from. Flake, Magnetsysteme. They mostly have things like magnetic lifting magnets or magnet grabbers, but they also have these magnet vises. So yeah, that's my little show and tell here. So over here at the surface grinder, I have another drill press spindle that I had in for reconditioning. Well, in this case, I'm only grinding the taper. And this is from a drill press, which has a really, really big quill diameter. And my V-block is on the edge of holding this in a reasonable manner. I'm riding the top edge of the V-block, and this is really not ideal. So the magnetic holding strength of the V-block is anemic. But the chain vise grip came to rescue. I purchased this quite recently because I didn't have a large oil filter wrench to grab stuff that hasn't flats. And I have torn apart many of the belt wrenches that have a textile or rubber belt that slings around your work, and I figured that a chain vise grip will do better. But it also turns out it's quite useful to fix or to clamp stuff to each other. And here it's used for work holding. I'm pulling the quill into the V-block with the chain vise grip. I have 1 millimeter rubber and some brass shim stock to protect the quill, of course. I don't want to put chain marks all around it, but worked really, really well. I have a sawn apart cordless screwdriver back here with 3D printed flange. a pulley that's pressed onto a 1/4 inch hex bit or driver, O-ring stock as a glued together, super glued as a large O-ring as a drive, and I have a pulley that's pressed into the end of the spindle in this case. And I'm just running it off a lab power supply. This is the, so I pulled the chuck off to show you the finish on the taper, and there is one spot in front here that I could not clean up, otherwise the chuck would ride too far back and I would have to remove, there's a thread back here, and I would have to remove parts of the thread to get the taper back far enough so the chuck can fully seat. I didn't want to do that. I think this minor left damage will not cause problems, but leave more material of the spindle intact. But the overall finish of the grind, this is done with an 80 grit Norton 3 SG seated gel wheel. And these do really well on cylindrical grinding on this machine. This is usually my go-to wheel for round work. And I'm spinning the spindle by hand. And this is quite decent. I would have to get the electronic indicator, but that's living over on the lathe and I'm not really too keen of ripping it out there. This 10 micron indicator reacts very, very well to small movements, and it's barely showing a needle movement here. So this is plenty good for a drill press spindle. And yeah, the indicator is touching indeed. And this indicator base is not as stiff as I would like it to be. It's repeating quite well, but when you hit it from different orientations, it will move. So you have to be a little bit careful. So that's basically all I have for this video. All that's following now is just blah, blah, blah. I announced in one of the last videos that I'm going to the USA for a 1-month vacation, and already had the flight booked, flying into New York and flying home from San Francisco, but I'm not going. Watching the news doesn't make me happy with planning this vacation anymore. Gives me a bad feeling, let's say it that way. So instead I'm going to Scotland for a month and I'm going to hide in a cabin somewhere. That's all I'm going to say about that. But I have to say thank you to all of you. The comment sections under the video is, well, under all of the videos, is super, for the most part, super polite and very friendly and very, let's say, focused on topic. I know that I get sometimes a little bit abrasive and almost like a jerk in the answers of the comment, but that's, well, I'm a flawed human. If you read the same comment of what you did wrong for the 20th time, it gets to you, and it's hard to not be influenced by that. That's strictly a me problem, of course. That's not the fault of the commenters. So yeah, I try to get better about that. What's really helping the channel, of course, is all of you who are monetarily supporting me on Patreon. This allows me to stay away from product placement, brand integrations, brand deals, paid product reviews, but still take time out of my day when I could also be making customer parts and make those videos and create hopefully educational and inspiring content for a wild mix of persons. I know of hobbyists and professional machinists that are in their skill way above what I do watching these videos, and I'm really grateful for that. So yeah, thank you all for helping me out there. Thanks for making this possible, and That's all I can say. Thank you for watching, thanks for your support, and I'll be back.